So I'm recording now. So now the secret of understanding the infectious disease modeling is to understand the normal curve, the normal curve for an epidemic. That's the secret. So this is the normal curve of an epidemic. So this is time, let's say in days, okay? And then this is the number, okay? All right.
Excuse me, Dr. Anthony, your voice is breaking up. I don't know if it's just for me or for everybody else.
It's
Can you
everywhere.
hear me clearly, please? Can you hear me clearly, please?
Yes,
It's breaking.
now.
Is it very
It's
clear now?
breaking. It's
Is it very
okay
clear
now.
now?
It's okay now.
Is okay now?
Yes.
All right. So I said,
Better.
okay. So I said, understanding infectious disease modeling, the secret is understanding the normal shape of the epidemic curve, all right? And the graph I'm showing you here, this is the time in days, and then this axis is the number of people that are infected.
Sorry, I can't see any graph.
Are you not seeing my Microsoft Word?
I'm not.
Hello, can anyone see my Microsoft Word screen?
We can see your screen, sir.
I can see it. Clarissa, maybe you should
You
refresh or
can log out
something.
and log in again.
Yeah.
You can log out and
Thank
log in
you.
again. Okay, so can you log out and log in so that I can approve you immediately?
Yeah, I think she's gone out, so shortly she should join.
Okay. Have you joined? Admit, okay. So please pay attention. Oh, it's very, very important. Pay attention now. So
Same thing.
now,
Same thing.
now this is what?
Same thing. I can't see.
It's not for my own it's not for my own end now, because I'm sharing my screen. Okay, let me stop sharing and share it again.
Clarissa, what are you seeing? Let's know if it's the same thing you are seeing.
Nothing. It's just the names and everybody.
So he has logged back. He has logged out. So let's see when he logs back in.
I'm going to share it again now.
Yeah, I can see it now.
Can you see it now?
Yes.
Okay.
Okay, so can you mute your mic, please? Mute your mic.
Yeah.
All right, so the normal curve of an epidemic. The normal curve of an epidemic. Who is joining? The normal curve of an epidemic. You see, when there's an outbreak, the number of infected cases will rise and reach the apex, right? And then as public health interventions are initiated, the number of cases will now start doing what? Dropping, right? Now, I hope you can hear me.
Yes.
All right. So now the rate at which the infection is rising, the number of persons that are being infected at every point of time is given by the formula B I B S over N times I. Now, this formula is going to give you the number of persons that are being infected as the case is rising, as the cases are rising. Now, I'm going to interpret what B, S, and I means. The B stands for the contact rate, the rate at which infected persons contact other people. That is a B. Whenever you see B in the exam, know that B means contact rate. So I'm trying to use simple words without so much English. Contact rate, the rate at which the infected person is contacting other members of that population. Now, for example, how will you interpret B? It means that an infected person will contact 0.3 number of persons per day. That is the meaning of B. Whenever you see B is equal to any number, that number is on the average, the number of persons that somebody that is infected contacts in a day, right? Now, the next thing we have in this variable is S. S means the number of people that are prone to the disease, the number of susceptibles, okay? So those that are prone to the disease, that is S. While our N means the total number in the population. So susceptible persons, those that are prone to the disease. While our N is the total number of persons in the population as a whole. Now, our I simply means the number of persons that are infected. Okay? So now you will see that when the number of cases are rising,
Sorry,
you
Dr.
see,
Anthony,
hello?
can you please say that what does I means in the formula?
I said I means the number of persons that are infected. The number of persons that are infected, that is I. All right? Now, when you reach here, here is called the peak. Here is called the peak. That means the apex. So now, at the apex of the epidemic, you will see that the virus cannot see any other person it can infect. There is no other person that it can infect because all the people here, they are either they have recovered or they are immunized. So that is why you have your small letter R. Your small letter R is called the recovery rate. So let us look at R. So when you have a small letter R, and let's say your R is 0.2. Now it means that the recovery rate is 0.2 persons per day. Now that means that 1 over R number of persons will recover in 1 day. So this is the correct way to interpret your R. If you want to know how many persons will recover in a day, just invert your R. That is 1 over 0.2. So our 1 over 0.2 now will give us what? 5. So that means that what? On the average, for this epidemic, 5 persons normally recover in 1 day. That is how to interpret your R in simple English, in simple language. Now, for us to know the number of persons that are being recovered from this epidemic, we need to multiply our R by the number of persons infected. Remember here, we multiplied it by I here, right? So here also, we're going to multiply it by the number of persons that are infected. So now, so you can see the two major sides of the equation. Here, the number of infections, the number of infected persons are increasing, right? Until it reaches an apex. Now, due to public health interventions, people start recovering, or some people start dying. Now, the number of cases will now start what? To reduce, right? So, for us to know the number of persons that are remaining, the number of persons that are remaining infected.
Sorry, excuse me. Excuse me, please.
Yeah.
So, you said when they begin to recover due to interventions, you said we're going to multiply what by R?
You
What are we
multiply, I'm saying that the number of persons that are being infected at any time is given by this formula here.
Yeah, sure, I got that.
ES over N times I. Why the number of persons that are recovering at any particular point in time. Remember that some people here are infected, right? So
Yeah.
this R is the recovery rate alone.
Yes.
R alone is the recovery rate. So if you want to know the number, you have to times your R by I to know the actual number of persons. Remember, yeah, so this I is derived from the number of the infected persons. So those infected persons, the number times the recovery rate will tell us the actual number of people that are recovering at any given point in time. Is that clear?
Yeah.
So once you have this picture in your mind, you can now derive the SAR model, the SIR model.
So which one is now 1 over R? Because you said 1 over R will now be
the number of days
people that will recover in a day.
Yeah, I'm coming. So now this R is a rate itself. Okay. Now the 1 over R stands for the number of days.
All right.
Before somebody recovers. The
number of days.
Yes. But the number of days it will take before somebody recovers is given by 1 over R. So now the secret is to just write out these formulas and just keep it, if possible, memorize them, because any question they will ask you, you are going to use one of these formulas to derive it. Okay. So now another formula I want you to know is we called effective period. Effective period. When you hear the word effective period, so when they say hello.
Yes, we can hear you, but your voice is going off and on.
Oh, sorry, I'm really shouting. I'm really shouting. I'm really shouting so that my voice will not be blamed. Okay, so I said when you hear the word infective period, the infective period simply is also the same as the duration. Remember, I said that 1 over R, that means 1 over, let's say 1 over 0.2 means that after 5 days, the person will now recover, right? So that 5 days is actually the infective, is also the same as the infective period. So the infective period means that the time at which that person is still infectious, right? So after that infective period, that person now recovers. So when you're seeing 1 over R, so when they say the effective period of something is 0.2, it means that what? You just invert it, okay? So it means that, sorry, okay, yeah, it means that 1 over R, that means that the infection will last for 5 days. And that is also the same as what? That the recovery period is what? 5 days. So it should take up to 5 days for the person to recover from the sickness. So is that clear?
No, it's not clear.
No.
Explain this effective period again, please.
The effective period, please.
What I said is,
Dr. Anthony,
what I said is that the
Dr.
effective
Anthony,
period is the same as the number of days the person will stay before the person recovers. So it is the same thing. Effective period is equal to 1 over R. That's what I'm saying. So they are the same thing. Either you call it the number of days somebody will stay before he recovers, which is equal to 1 over R, or you also call it the effective period, which is equal to 1 over
Is
R.
this the same? Is this also the same as recovery rate? Because before
Yeah,
you
no,
mentioned 1 over
no,
0.25 people will recover.
no. The recovery rate is R itself. Okay, when you invert the recovery rate, you will get the recovery period or the effective period. Is that clear now? So the recovery period, 1 over R, is the number of days the person will stay before we recover. Okay, and that is also the same as the effective period. Okay, is that clear?
You said that's also the same as what?
Effective period, they are the same thing. No, 1 over
Effective
R.
period
Effective
and what?
period.
Effective period
period.
is also known as the number of days the person will
Days.
stay
Okay, yeah.
before we
Okay.
recover. They are the
Yeah.
same thing. So if I
That's
have
1 over
COVID-19,
R.
So 1 over
yes,
R is equals to effective period. They are the same thing.
Yes.
Saj, you wanted to say something? Saj.
Yeah, that's fine. I understand now.
Okay.
Okay, all right. So we have gotten our contact rates, we have gotten our infective period. So the next thing now is I'm going to clear my screen. I'm going to clear everything I've written now. Let's look at the SAR model. Okay. So
Please, your voice is going on and off. Can you be kind of?
okay, so you can hear it clearly now. Sorry. Okay, so now you have the SAR model SIR. Okay, so everything here is happening at the same time, right? So those that are prone to sickness, that is the S, those that are susceptible, are being removed from the population. So that being removed, if you remember our what we drew before, remember the diagram we said BS over N times I here, okay, and then we said here is what arrow times I, right? So now the number of persons that are being removed from the population, why you see that negative sign, is because it is showing the direction. The negative sign you are seeing, like in your notes, you see BSI is showing a negative direction that something is being removed from the general population. Okay, so some people as those that are prone to sickness are being infected. Those that are infected are also recovering or dying. Okay, so this is just a basic explanation of SAR model without mathematics, without so much wahala of mass. Okay, so some people, those that are prone to infection, that's the S, over time they are being infected. That means they are being converted to I, right? While those that are infected over time, they either die or they recover. Okay, so for us to now derive the ultimate equation in simple mathematics, for us to derive the ultimate equation for the SAR model, remember we said our formula. Remember I drew this thing, so we have B S by N times I. That is for as the inflation is rising. While as the inflation is going down, you have your R times I. So now we want to derive the SAR model. Okay, we want to derive the SAR model. Now I said at the peak here, at the peak of infection, the rate at which the infection is rising, okay, is also equal to the rate at which people are recovering. So at the peak here, the next formula we need to know is that at the peak here, you will see that our B over R is equal to our RO. So what this means is that the rate of transmission, which is equal to the contact rate, this B is the contact rate or the rate of transmission, right? The rate of transmission of the infection is equal to the rate of recovery, and that is equal to 1. Now, this equation is something you need to write down. This particular equation is something you need to write down. At the peak, at the apex, here, when the epidemic reaches its highest level, before falling down, the rate at which the infection is being transmitted, that's the contact rate, or you call it the transmission rate, is also equal to the rate at which people are recovering or they are also immune to the sickness. So such that that rate becomes our RO, and that rate is equal to 1. So you need to write down this particular formula. So this will now help us. Hello? Hello?
Hi.
Can you guys hear me clearly? I'm shouting.
Yes, we can hear you.
Can hear you.
Okay, so do we understand that at the peak here, at the peak of infection, the rate of infection is the same as the rate of recovery? The ratio between the rate of transmission or the contact rate is also the same as the rate of recovery. And that will give us our RO. And that is equal to 1. Do we get this one now?
Yes.
Okay. So now if we understand this right now, so we are going to now write the equation of this SIR model, the equation of the SIR model. So if we take the infection, the number of infectives for tomorrow, we will say so I T plus 1. This represents the number of people that will be infected by tomorrow. Okay. Now, minus the number of people that will be infected today.
The line is breaking. No.
Can you guys hear me?
No.
I want to. Can you hear me? I'm shouting. Hello.
Dr. Anthony, we can hear you for a while, then it goes off, then we can hear you, then it goes off. So it's breaking basically.
Okay, that's network. Okay, I'm sorry for that. Okay, so what I'm saying now is that having explained all these things now, I want to write the equation of the SAR model in normal mathematics, okay, in simple mathematics. So on the screen, our I here, I in bracket T plus 1 means the number of people that will be infected tomorrow, okay, minus the number of people that are infected today. So that difference, we want to be able to predict the number of people that will be infected by tomorrow, okay? So this difference is given by, if you remember our formula at the top here, if you remember the formula we used before, it is given by what? BS over N times I. That is when the infection is going up, right? When the rate is rising, okay? Then you now minus the number of those that are recovering. So minus arrow I. So this is a simple equation of the SAR model without it being complicated. This is a simple equation of the SAR model without it being complicated. Now, from this equation, can you guys hear me, please? It looks like the line is breaking.
Yes.
You can hear me clearly, right?
Yes.
So do we understand the whole how we derive this formula now? The difference for us to know the number of people that are being infected at every time, we need to get first the total number of people that are infected, right? And then with minus the number of people that are recovering from them. That will tell us the balance. Okay. So this is the balance that is remaining here. So this is the simple equation of the SAR model. In fact, you have to memorize this equation. So
Okay, please, I want to ask.
Okay,
Okay, so
go ahead.
when you have this kind of formula, for example,
Yes.
and you have all the figures to impute for the parameters and you get an answer, how would
Now,
you interpret that
Now,
answer?
the answer, remember, this is a difference. So this is different between number infected tomorrow and today. So,
Right.
so the answer is what? This thing is what? The number of people that are infected at any particular point in time. That's
Okay.
the meaning of this. Okay. Now, why this is in simple mathematics. Okay. If you want to write this thing in complex mathematics, now I'm going to change this equation now into the I, okay, over. I'm going to change. Oh my God, this thing is breaking. Let me clear my screen. Sorry. So now I'm going to write the normal equation. The normal equation I wrote now is in terms of in simple mathematics. I said the difference between tomorrow, those that are infected, and today is equal to BS over N, okay, times I, then minus arrow times I. Okay. So now, if you factor out I from the equation, if you bring out I outside the brackets, you will have BS over N minus R. So that will give us the number of people that are infected at any particular point in time. Okay. Okay. So I was now saying that if you want to write this mathematics, this simple mathematics now in a more complex way, using all those derivatives that you are seeing, what we will do is that this our n is here will disappear. This n that I see here is going to disappear. So this difference here is what the mathematical people, the mathematicians, what they now call our di over dt. Okay, so this is the relationship. So this thing here is the same as this. Okay, so when you use derivatives, then you can now eliminate all those things. So now where we have bs over n times I, you simply have what? You have your bsi, okay, then minus arrow I. So this is the same as your SAR model. So this thing here is the same as this first equation. So, but the one I want us to know, the simple one I want us to know is this first one. That's the one that you need. This one, if you know mathematics well, you can use it too. But the main one is the one I want you to know. So let me write it again. The main one is the difference between tomorrow, that's those that are infected tomorrow, and those that are infected today, is given as
the T stands for today and tomorrow.
Yeah, yes, exactly. The number of those infected tomorrow at the time tomorrow, that's T plus 1 is tomorrow, while our T is today. Okay. So the difference is given by BS over N times I. Okay. That is those that are infected, total infected, minus those that are recovering, which is given by R times I. This is the only equation I want you to know. Just only this. Forget about any other complex mathematics. So if we filter our I from this equation, you will have your BS over N minus R. And this becomes our ultimate formula for the SAR model. Okay? So this means that if we now want to know what can we do to stop an epidemic, is it to increase our R or to decrease it? So you can see that at any point in time, the difference, the number of people that are infected is given by this equation here, right? Okay, so that means that we want the difference here to always be on the negative side. That means we don't want anybody to be infected. Okay, so if you don't want anybody to be infected, what are you going to do as a public health, as an epidemiologist? What are you going to do so that this equation can become negative? Remember, assuming that you have 5 here, it means that 5 people are infected, right? Assuming that we do the calculation and we have 5 here, it means that 5 people are infected, right? Assuming that we have 0 here, it means that nobody is infected, right? Okay, so now if we want this thing to move to the negative side, so that the number of those that are recovering will be more than the number of those that are infected, what are we going to do to our R? What are we going to do to our R here? Remember, this thing is minus, right?
Divide by 1.
No, now what we will do is to just increase the value of R. That's all. Increase the value of R. Remember that assuming that PS over N is 5 now, and then our R is 4. So everything here will be 5 minus 4. That'll be 1. So we still have people that are infected. So for us to stop the epidemic, we want to make sure that this equation is either 0, that means it is at the peak, okay, or is on the negative side. So that the number of those that are recovering will be more than the number of those that are infected. I don't know whether we understand what I'm saying. Do we understand what I'm saying? Or please, or because everything we are doing is dependent on this thing, I'm doing now. So I'm writing the equation again: ds over n times I minus r times I. I said that this difference here is the number of people that are infected at any point in time. And this is the equation of the SAR model. So if this equation results to 0, it means that what? We are at the peak. Okay, that means what? That there is equal balance on both sides. Is that clear? Hello?
Yes.
Okay, so if this equation results to let's say 10, so it means that we have 10 people that are infected at that particular point in time. Okay, and we want to stop the epidemic. We don't like it like that. Okay, so what do we do to get our epidemic under control? We want this difference to turn into what? Negative direction. So that means there is no body that is infected. Okay, so and for us to do that, we have to increase our R. So let's say this one is 5. So if we make our R like 8 now, you will see that this will become negative. So that means we will have more people that are recovering. Are you seeing it? I hope we are understanding. Hello.
Please take this line again. That if we want anybody the people that are infected at any point in time, if you want it to reduce, or if you want it.
Yeah, okay. If you want it to reduce, you have to now increase the number of the number of people that are recovering. That is RI. Now you have to increase your R. Remember, this I is same for both sides, so it's not significant now. So what we're looking at is the R. For us to make this equation to become negative, you have to increase your R. Okay. So that is public health prevention programs are targeted at 3 things. So you can write it down. Public health interventions are targeted at 3 things. Number 1 is to what? Increase our R. Okay. Then number 2 is to reduce our contact rate. That means reduce our B. That's this one. And then number 3 is to reduce the number of what? Susceptible persons. So these are the 3 main purposes of public health intervention. So if you increase our R, remember our R is what? The rate of recovery, right? So
Dr. Anthony, just one question.
Yeah.
There's another R as well, the big R. That is different to the small R, right?
Yes, I'm coming. Just calm down first. Let us understand this one. This one is the most important.
Okay.
This what I'm saying now. You can derive all the answers to the questions from this formula. All right. So understand the 3 main purposes of public health intervention is to increase our recovery rate. And when you increase your recovery rate, what will happen to the number of days that you stay in the hospital? Hello?
You said if we
It will reduce.
it will reduce.
Good. So that will decrease our number of days in the hospital, right? Okay. So that will decrease our hospital admission days. All right. So increasing the recovery rate will reduce the number of days that someone stays before the person will recover. I hope that is clear. I hope this one is clear now.
That's clear. That's clear.
Yes.
Good.
The number.
Yeah. Okay. Now decreasing. So how can you increase recovery rate now? By giving what? Medications, like by giving drugs, right? By giving fluid. So all those public health interventions that are aimed at treatment, they will help us to reduce. So they help us to increase the speed of recovery, to increase our R. Okay. Now our B is contact rate or transmission rate. So what can we do to reduce the transmission rate of COVID-19? For example, what we will do is what are the things we can do to reduce the transmission rate of COVID-19, the contact rate of COVID-19 virus?
So these will be public health measures like wearing face mask,
Face
isolation.
mask, isolation, lockdown.
Lockdown.
So hand washing, wearing face mask. So that is B. We are reducing B. As you can see here, when the numerator is small, can you see? So you are reducing the numerator here, making it smaller, and you are increasing your R here, making it bigger. So that is the aim of public health intervention. Then the last one is to reduce the number of people that are susceptible. That's those that are prone to the disease. And what can we do in public health to reduce the number of people that are prone to the disease? What can we do?
Vaccination.
Immunization or vaccination. Exactly. So that's the domain of immunization or vaccination. So take this thing and write it somewhere, memorize it anyhow you want to do it. That is the relationship. When you increase R, the number of the recovery days will always what? Decrease. So take note of that relationship because it will help us to solve some problems. All right. So having said this, let us now go to our RO and RE. So I gave you a formula. Our RO is given by, it occurs at the peak. So at the peak, the effective rate is the same as the recovery rate. Okay? At peak. Okay? And that will be equal to what? 1. The ratio is 1. So when the RO is 1, it means the epidemic is neither increasing nor decreasing. Okay? Now, when our RO is less than this ratio here, when our RO is less than 1, okay? When it is less than 1, that means what? This guy is what? sorry, when our RO is less than 1, that means that our R is bigger, right? That means that people are recovering faster, more than they are being infected. Okay, so our ratio will now be less than 1. Okay, so that will not give us what? So, and that will not, that's the main aim of our public health intervention. Okay, to make this ratio less than 1. If it's less than 1, it means that the epidemic is what? Going down. The epidemic is going down. Okay. Are we getting how I'm deriving all these things? Do we understand this last part?
No,
I did now?
no,
This
Okay.
board,
no,
can you this part again, please?
no.
All right. Okay. But do we understand up to here? Everything above this line, this equation. You
Yes.
understand this one?
Yes,
Okay.
Yes.
yes.
So let me clear my board. So I said at the peak, that means here, at this peak here, our infective, the rate of infection is, sorry, the rate of transmission is equal to the rate of recovery. So our RO, please mute your mic, please mute your mic. So our RO is equal to B over gamma, okay? B over gamma. So I was saying, using a normal language, so that means what? That our transmission rate is the same as our recovery rate. So the ratio is 1. At the peak, the ratio is 1. Okay. So if we want the epidemic to stop, which of these two are we going to increase? Is it the transmission rate or the recovery rate?
Recovery
Using
rate.
normal man sense. So we increase our R. As simple as that. So if you want the epidemic to stop, you increase your gamma. So that means that, and if you increase your gamma now, so let's say you have 1 over 10. So your B is 1 and your R is 10. Is this less than 1 or more than 1?
She's
Less than 1.
less than 1.
Simple. So that means that if you want to stop the epidemic, if you want to stop the epidemic, you want to make your RO to be what? Less than 1. That's the whole that's the summary. Okay. If you want the epidemic to progress, you have to now increase the transmission rate more than the recovery rate. So if you want your epidemic to progress, you have to make your RO to be what? More than 1. I hope it's clear. I hope it's clear now. Is it clear?
Yes.
So
Okay.
Not completely.
Okay. Ask your question.
Yeah, the last part you said about the RO, that if you want to stop after you said if you want to stop the epidemic, that
Yeah.
it should be less than 1. Then the other
Yeah.
part you mentioned, that's
It's just the opposite now. If you want
okay.
if you want the epidemic to continue, you
Okay.
make your transmission rate more than
Okay.
1.
Okay.
So okay. So
Okay.
so this is the formula for RO. Now the question is, what does RO mean? RO means the number of persons, the number of persons, sorry, the number of secondary infections. The number of secondary infections. Okay, that is transmitted by an infective person. So that means that if someone is COVID-19, the number of persons that person will give that COVID-19, assuming the main secret here is assuming that 100% of the population is susceptible. assuming that 100% of the population is susceptible. So in this RO, the assumption is that all members of the population are susceptible to the disease. And we know that in the real world, it's not everybody that is susceptible to the disease. Even in COVID-19, it's not everybody that got it. All right. So RO is assuming that every member of the population is susceptible to the disease. So take note, if you don't put this susceptible in your definition, you are failed it, because the difference between RO and RE, that means the effective transmission rate, is just this word, susceptible. Yeah. So in RO, we are assuming that every member of the population are susceptible to the disease, which doesn't exist in the ideal world. It's not in the ideal world. It's not everybody that will be susceptible, because some people might be immunized. Some people can be infected and they recover. You understand? So RO doesn't really apply. It's just like a mathematical in the mathematical world. Yeah, everything is ideal. Okay. All right. So
I have a question, please.
Okay, ask. Go ahead.
Okay, so this definition now of RO, because I already jotted down something you said earlier. You said at the peak of an infection, the rate of infection or transmission is also equal to the rate at which people are recovering, and that is RO.
That is okay. Yes, that is RO. Yes. Remember, see, hello.
Yeah, I'm
I
with you.
said the ratio between this and this is the RO. Okay. So now RO is defined as the number of people, secondary infections, that a single case infects in a population where where 100% where everybody is susceptible. Okay. So in a population where everybody is susceptible, the number of persons someone can infect, okay, that is given by by this RO value. Okay. So can you ask the question now if you have a question?
I don't want to get confused.
Confusing already.
I don't want to get confused, because what you said earlier was that what you said earlier was at the peak of an infection. Of course, I know at the peak of an infection, the rate of transmission is the same thing as the rate of recovery, right?
Yes. Now it means
is
that this P
RO.
over R is equal to 1.
Okay, so now this is just okay. So now this definition you are giving us is just to put it in English, Abby. That first definition is a mathematical definition, if I can say that.
I don't know. Exactly. I don't know how you are understanding it, but they are the same. Yes, they are the same. So at the peak of the version, you have that RO is equal to 1 at the peak. Okay. So once you start getting to this side, is to start becoming less than 1 on the right side. But here is above 1 because the epidemic is going up. Okay. So at the peak, it becomes 1. Then on the right side, when everybody is recovering, it now becomes less than 1. So that's how your RO moves around.
I think this one makes more meaning. The definition is very, very confusing.
Exactly.
Okay. So I will still check it. I will still check whether RO is it per day. I don't know whether there is anything like per day in that definition for RO. You can check. Is there anything like per day in that definition for RO? I don't know.
Where are we supposed to find it?
Internet now. just type in basic.
Internet for now.
All right. Please listen. Let us derive the other one. Our effective reproductive number, RE. It can be RE. So, like I told you now, RO is assuming that everybody is 100% prone to the disease. But we know that in the real world, it's not like that. Okay. So how can we get our RE? Our RE is equal to RO, okay? RO times the fraction of the population that is susceptible to infection. So write this formula. This is your RE. So S over N means what? The number of
Too many formulas now. Which one to remember?
just, if you go home, you practice this thing, you understand it. So our RE is
We're home.
RO, okay, times the fraction of the population that is susceptible to infection. And that fraction is given by S over N. That means number of susceptible persons, okay, divided by the total population. So that's how you calculate your RE. Okay. Okay. That's how you calculate your RE, effective reproductive number. So in case in exam you see RE, just bring out this formula and keep it by the side.
You say this RE, sorry, is effective what?
Effective reproduction. Whether it's reproduction number. RO is
effective reproductive number.
Okay, effective reproductive number. While RO is basic reproductive number. That's the basic in an experimental world. Okay. So the last equation we need to know is the equation for herd immunity.
Sorry, please, before you go to equation for herd immunity,
Yes.
the RO, I want to just get that equation. I think I didn't, I just wrote out the words, but I didn't get the equation correctly.
RE or RO?
RO, the basic reproductive number.
Okay, the basic reproductive number. Okay. At the peak, you have to add this word. It's only at the peak. Oh. So at the peak, RO is equal to beta over gamma. That means the rate of transmission divided by the rate of gamma. Okay, and that is equal to 1. At the peak, only at the peak. Oh. All right. Are you getting me?
Yes.
So this is the equation you need. So from here, you can derive other ones.
Okay.
If the epidemic is progressing, that means this our B is very large. Transmission is happening faster. So our RO will be more than 1. If the epidemic is going down, this our gamma is larger. So our RO will be what? Less than 1. So this is the equation you need here. But make sure you add okay, equal to 1. All right.
Thank you. Yeah.
Okay. So then the last equation we need to know is the equation for herd immunity. All right. So it's you to calculate what fraction of the population needed to vaccinate, okay, to achieve herd immunity. Do we know the meaning of herd immunity? Herd immunity means the immunity that is conferred on uninfected persons as a result of what? The vaccination of every member of the population. As a result of the vaccination of other members of the population. So for you to calculate herd immunity, take note I said the word fraction, or it's fraction. Okay. So if you want to calculate this fraction, so let's say there is COVID-19 outbreak, okay, and you came as an epidemiologist, and they ask you to calculate the number of people that we need to vaccinate in order to stop the COVID-19 spreading. That formula is given by 1 minus 1 over RO. I don't know how they derive the formula, and I don't care to know. All I know is just to know the formula. so, so 1 minus 1 over RO will give you the fraction of the population that you need to vaccinate in order to achieve herd immunity. Remember, it's only a fraction, okay? So if they now ask you to calculate the actual number of people to be vaccinated, okay? So it will now be what? 1 minus 1 over RO, okay? Times the total population, which is N. As simple as that. So this will give us the actual number of people to be vaccinated. This formula now. That means the fraction of the population that you need to vaccinate times the total population. Okay. So this brings us to the end of the SAR model. So we'll just go straight to answer the questions now. Any question at this point? Hello?
Yes, please. Can you just recap on this herd immunity again?
See, okay, I said the fraction of people that you need is given by 1 minus 1 over
A bit oft.
of 1 as a whole number minus 1 over RO. So if you see a question and they give you the RO itself, and they ask you how many what percentage of the population do you need to vaccinate? This is the formula. Okay. So if they now ask you the number of people that you need to vaccinate in order to achieve herd immunity, you just take this formula and then times it by the total population. That will give you the number. Okay. The number of people that you need to vaccinate to achieve herd immunity. Okay. So this brings us to the basic, at least this brings us to the end of all this derivation. Okay. So any question at this point before we attempt the questions that they asked here, the first question. Any question here?
I think if you start the questions, it will probably make more sense.
Maybe.
Yeah. Okay. And so let me go. I hope you can see my screen. You can see my
Yes. Yes.
So all these ones are simple ones. Let me just go straight to the I've already answered all of them, Sha. So let me go straight to that one.
Is this our question? Any of our past questions, Doctor?
Yes, so it is.
Really?
Please, can someone send me that material that has the SI model? It's not in this one, no. I don't know where.
All the things you are teaching us, are they answers? Are they answers to some of these questions?
Yes, they are the answers to some of them.
Chimo.
So just a minute, let me get the question, the one that has some model.
What is Chimo?
My God. Eh.
Ibalada. You say nothing. Eweleke.
Oh God.
God will help us.
Amen.
No. Let me get the stuff. Mock exam. Okay, I think it should be this one. See, just spend time with the family. You understand it. It's simple. If you watch this video again, I'm recording this video. So if you watch it again, Just try and derive it with your brain. By the time you practice it 1 or 2 times, you will master it. You don't need to ask so much questions. So let me see whether I will see that one. Yeah,
Eh?
I have seen it. So let me open it. Okay, so for this, I hope you guys know these ones now. All these ones, relative risk and all these ones. Okay?
No one is small though.
Ah, okay. So question number 2. Can someone attempt? Having done all this mathematics now it's time for application. Okay, so having done your practice, now we are in the ring now. Where is that? That's number 2.
It's time for boxing now.
Yeah.
Yeah. Answer. Explain the difference between RO and RO number. Sorry, the difference between RO number and RE. It's supposed to be RE for a pandemic. Okay, so there is an outbreak of a disease among 100 people in a town of 1 million people. So it is known that the RO for this disease is 1.06. Okay, and the average generation time for this disease is 5 days. So all these maths that we did now, so we will write our B. This is disappearing. B.
RO number.
My marker is disappearing. I don't know what is going on. I don't know why it's disappearing.
For this question, is it just a basic answer, using non-maths?
Yes. So
So,
how will you
this,
interpret our RO here?
the RO is the secondary infections. Each infected person is committing, and the R is the recovery number.
So, but then he said that the RO is 1.06.
Where are you taking us?
I'm trying. I can't even.
Can you see my screen?
Yeah.
Logo.
Good. So it says here the RO is 1.06. So how will you interpret this our 1.06? That's
Means
the question.
the rate of transmission is higher than recovery rate.
Correct.
Each person is infecting 1.06 people.
What? Can you come again?
And each person is infecting a further 1.06 people.
Each person is infecting on the average.
Okay, 1.06 people. Okay. Your voice has totally disappeared.
Sorry, let's look at the definition of basic reproductive number. Okay, so basic reproductive number is the average number of secondary infections produced by a typical case of an infection where everyone is susceptible. All right. So, for example, if the RO for measles in a population is 15, then we will expect each new case of measles to produce 15 new secondary cases. So
That's what Saj said.
yeah, I'm agreeing to what he said. So that means that each case of the disease, the disease produces 1.06 other cases on the average. Okay. Now, what is the RE in this for this question now? How will you calculate the RE? Remember, in your RO, you must say, assuming that the whole population is what? Susceptible, right?
Mhm.
You must say that. Okay. Now, how do we calculate our RE here? What formula are we going to use based on everything I have shown you already?
This is RO times
O times S over N.
Okay, so RO times S over N. So what is our S now? Number of susceptible. Okay.
Sorry, Dr.
100.
Anthony, just one
Yeah.
second. This R, it doesn't. There's no E in there. So how do we know if it's R E or which R is
No,
this?
this is a mistake. He said what's the difference between RO and RO? Supposed to be RE. So it's a mistake here. Okay. So this should be RE here. All right.
Okay.
So now you are expected to calculate your RE and then make a comment based on the value that on the answer you will get. So how do we calculate the RE now? We have our RE as 1.06.
So that would be 1.06 multiplied
Yeah.
by 100 over 1. Is it 100 over 1
Million.
million?
Okay, so can someone punch that in a calculator? What's the answer?
I'm lost, so
Please, can the person answer this? Please, can you repeat your answer, please? So our RO is 1.06, and our RE should now be what? Our RO times S over N. So that will be what? 1.06 times our S is 100, and then our total population is 1
1
million.
million.
So if you cancel this thing, so we'll have one, two, so we'll have like 1.06 is 10 raised to power
Minus 4.
minus 4, right? So generally the effective reproductive rate is very, very, very small. It's infinitesimal. Okay. So we'll say that on the average, an effective case will infect this 1.06 times 10 raised to power minus 4 number of persons. That's we produce 1.06 times 10 raised to power minus 4 secondary cases. Okay, assuming in a population where how many percent is 100 over 1 million? On how many percent is 100 over 1 million now? That would be,
How many percent? I don't understand that.
I mean, 100 over 1 million. What will it give us in terms of percentage? 100 over 1 million
Okay.
times 100%.
Zero, 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 zero.
So we have like 0.001%. Okay, so in a population where 0.001% are susceptible. Okay, so I'm just trying to calculate the number of this percentage here. Okay, so on the average, a single case of that infection we produce 1.06 other cases in a population where 0.001% are susceptible. That's how we interpret it.
Mm.
Okay.
Oh, I'm more
Sorry.
confused than I started.
Yes, so how are you? Have to watch the video again. Then for number 2, I'm here to find out answer number 2. Okay, and then number 3, get the date, expect the number 1,000. I'm yet to get the answer. But at least
Sorry,
maybe
this
in a
sorry. Let me take
yeah.
you back. This
Okay.
2B. So what is the answer
2B.
now?
This one.
Yeah, the one you just did, the RE.
The RE is 1.06. Let me write it in a different page. The
Times
answer
10 raised
is
to power minus 4.
yes, that's the answer. The number
Okay.
of secondary cases that it will
Okay.
produce.
Okay, we're not attaching anything to it. We'll just put it like that.
Yes, nothing else now.
Okay.
What else will you put? Unless you want to write it in this amount 0.000. It will be a long stuff.
Okay.
That's
Okay,
what
but
that
this
man
is
taught
the
us.
formula. Okay, did you say you should write it in full fraction?
No.
No. I'm not talking.
No.
Okay.
Is this
So by the time we will do our next session, I'm going to get the answers for this one. So for now, this is where my knowledge has ended. Now, okay. So let me see whether I will see another one I can attempt. Okay, I think this is all.
Okay, so you have to attend all, oh. You
Yeah,
have to
so I will attend. No problem, ma. We will attend. All these ones I have attended to them. It's just remaining those two questions. Those ones are not as simple now. You guys already know these ones now. They're to teach you oscillation and native list.
You don't know it.
You know it too. You must know it too.
Hey,
Okay, so
just now.
now for you to learn, I've really done. I don't want this video to be too long. Done with, I've done a detailed video. In fact, several videos already on oscillation. All this.
We can't hear you very well again.
I said I have already done a detailed tutorial. So if you log into your back end, if you log into your course now, I've done a tutorials on every other thing in this question apart from these two questions here. Okay, so this one, maybe our next meeting we'll attempt this one. I've already answered all these ones already. These ones are simple, so they are not my issue. Let me see whether I will see any epidemic, whatever. Simple things. So, okay, yeah. So look at this one here. I've seen somebody here now. Okay, so now can you see number 4? So in the SI epidemic model, a key factor driving the number of infectives. So this one will require that you write out all the questions that you know.
All the what?
Driving equations that you know before now.
Okay.
So that's the purpose of all those things we are doing, all those drilling we are doing now. So a key factor driving the number of infectives to be expected in a community at a particular time after the epidemic starts is the contact and transmission rate. And that is what our B. Abi?
Yep.
Which should be different for each epidemic. Now, they said, name 2 quantities that control the contact and transmission rate. Now, if you remember our formula, we said our formula is what? Bs over n times I, okay, minus gamma times I. That's the formula to know how many people that are infected at any point in time. This is a formula to know how many people that are infected at any point in time. All right?
Yeah.
So now from this formula now, what are the two quantities that control the contact and transmission rates for a particular disease?
Number of infected.
Huh?
Number of infected people.
Wait. Let's finish. Let's get all the formula we have. We have B over R is equal to RO. At peak,
Yeah.
okay?
Yes.
At peak. So between this one and this one, which one seems to be the most likely answer in this one, this question?
The first one.
The
B
first one.
S over N.
Wait. This is the change in the number of infected, Abi. That means yes, today, tomorrow minus today. That's this one. So this one is giving us the number of infectives. So now it said a key factor driving the number of infectives to be expected. A key factor driving the number of infectives to be expected. And this thing here is what? This one. Are you seeing that?
Yes.
So this tells me that this is the equation that they're talking about here.
Yes.
Okay. So
Like.
that says name two quantities that control this our B. So from here we see that our B is dependent on S and I. Abi? And
Yes.
even N. There are even three things here.
Yes.
Okay. Okay. So that gives us the answer. So I will take the total number of the number of those that are susceptible and the number of those that are infected at that particular point in time. All these ones are in the lecture notes.
Number of the population could also be.
And we're coming now. Let's go to the next question. Look at it here. Name the additional factor that is needed to model.
Now, wow, for this Ogajono.
So the thing is that there are three things that are needed. Okay. So that will be what S. All right. So you can answer B and S in the first one, and then come here and answer I. It's the same thing. The main thing is he's trying to check whether you understand this SAR model. Okay. Now, in the SAR epidemic model, it is not generally possible for an entire community to become infected. Okay. What equation comes to your mind now, based on this first line?
That second equation you wrote.
The RE.
Wait.
R.
Yeah, is that? Okay.
That second equation
is equal to RO times S over
N,
right?
Yes.
Good. Okay, so what is the key quantity that describes the proportion of the community that might eventually be infected? So you see, this answer is wrong. So it's not carrying capacity. This is when I was still trying to understand the question. So that's not the answer. By that time, I was still trying to read. I was cramming. So so now, so this is the answer here. So he said, what is the key quantity that means the proportion of community? I seen S over N.
Sorry, excuse me, please, but it's actually carrying capacity he gave us as the answer.
I've removed it. That's a mistake.
No, John himself, our lecturer himself. I mean the lecturer himself. Okay. Yeah. That's the answer he gave us. So if that's what you
let's read the question again. In the SIR model, it is not generally possible for an entire community to become infected due to some members of the population recovering concurrent to others developing the disease. What is the key quantity that describes the population of a community that may eventually become infected? This carrying capacity.
Yeah, I'm missing this due to some members of the
because
I didn't capture this part. So I think you know this answer I copied it from the PowerPoint. This was when I was still trying to understand the whole SAR model thing. So I just copied this directly from the note the way it is. So, but then I'm not trying to come up with another answer. So it said this is how it is in the note. Not all population will become infected. Okay. Then so N minus gamma over P over is not a current. Okay, so I didn't know this before. So add it to your list. So the total population, okay, minus the number, the recovery rates over infective rates will give us our carrying capacity. Okay, so I don't know much about the carrying capacity. Maybe I'll read this more. So I'm seeing another equation here. K is equal to N minus gamma over beta. Okay. Okay. So also the recovery model, it can predict the maximum number of infectives. So take note of this one. I don't know it before now. So I'm just seeing it now. Now you said It now said, beside the quantity named in C above. What's our C? Our C is this question here. Okay, this carrying capacity. Now, besides that carrying capacity, which additional quantity is needed in the SAR model to calculate the number of effectives? Let me see who will get it. Which additional quantity is needed in the SAR model to calculate the number of effectives? Look at our question here. Our number of effectives is what? BSI over N minus what? RI. Is that correct? Is that correct? What's going on now? See, it's
So
something.
confused, honestly.
What is confusing? What is confusing you now? He said, apart from carrying capacity now, apart from this equation here, N minus R over beta. Okay. He said, what other quantity is needed for us to calculate the number of infectives at any particular point in time? So, and I was telling you the equation now that I told you to memorize, which is the equation for SAR model. Anytime they ask you, if you don't understand this derivation, just know the simple one, which is what? The difference between those that are infected tomorrow, okay, and those that are infected today. That difference is given by BS over N times I, okay, minus gamma I. So this equation here is the same as this thing. They are the same. It's just mathematics. So this the I over the T is saying the rate of change. It's same thing as for every day. Okay, this and this are the same. Just that when you're using this our derivative, you remove this your N. This you don't take into account the total population. All right. So now they are asking, apart from carrying capacity, which additional quantity is needed in the SAR model to calculate the number of effectives to be expected? And I've already told you that the number of effectives is given by this formula, BS over N times I minus gamma times I. And if you remember, in the first question, we have already used BS over N to derive the answer. That's number 4 here. 4A. So the only thing that is remaining is our R
Time.
over I.
Tomorrow and
Okay.
today.
I can't see the screen again. No.
It's not my I'm still sharing it. Can you guys see my screen?
Yes.
Me, I can't see again.
You have to log out again and log in again. Let me approve you. Or let me stop sharing and share it again. Okay. So let me share it again. Hey, can someone add her? The person I just joined. Okay. All right. Okay. So
I can't see.
no, don't worry. I'm sharing it now.
All
So I was saying that the last question is, he said, beside the quantity named in C, that's the carrying capacity, which additional quantity is needed in the SAR model to calculate the number of effectives? And I've already given you the equation now. I said this one here is the same as this one. Either you write it like this, or you write it like this. If you know maths very well, you can write it as derivative. If you don't know maths, this is the simple equation here. All right. So the answer to this particular one is the recovery rate. That's the answer. So
We can't hear you again. No. Your voice has gone. No.
the answer is the recovery rate. So gamma. Remember, we have not mentioned gamma. Okay. We have not mentioned gamma since we're calculating all these things. So the answer is the recovery rate, because because you have to calculate the total number of those that are infected. That is BS over N times I. Then you will now minus the number of those that are recovering from the population. Okay. So I think that should be the last question. Okay. Then the last question here is in number E. Assume that for a particular disease, the infectious period is 8 days. What can we use to he said if the recovery rate is 0.05 and then at some particular time there are 1,000 infectives in the community, how many will you expect to recover? How many will you expect to recover? So in this question here, we are giving our recovery rate gamma, and our gamma is what? 0.05. Okay. Then we have there are 1,000 infected. So that's our I. Our I is 1,000. Okay. So in that said, how many will you expect to recover? Okay. So we know that using our expression, I for tomorrow, that's those are infected minus those are infected today, is equal to BS over N dot I times I minus R times I. Okay, so we know that those that are infected is given by BS over N times I, all right? And then we know that number of those that we recover is given by R times I. Okay, so here we are asked to calculate how many people will be expected to recover. So that would be what? R times I. That will be what? 0.05 times 1,000. So 0.05 times 1,000 will give us what? 1, 2. That will be what? 1, 2.
50.
So that will be what? 50. Okay. So that's simple enough. So here we didn't use this infection period here because they didn't there is nothing that is relating to it in this question. Okay. Now let me see who will get this one. This one is where I will know the real epidemiology. So give one reason why the fundamental assumptions of SAM model.
Have we finished the other one? Sorry.
Which one again? It has finished now. Which one are you talking about?
So we are not going to use this infectious period of 8 days at any point. Just
they have already see they have already given us our recovery rates here. So I didn't use it. So when they said that the infection, because now if assuming that they didn't give this our recovery rate now, even this question itself now, I'm questioning it because if I say infection period is 8 days now, okay, it means that after 8 days, the person will recover. Abi?
Yes.
Okay, sorry. No. Infectious period. That means the number of from the time the person was infected till the time the person transmits the infection to another person. That should be in your infection period. So I don't think is related to this question. And based on all the formulas that I already know before now, there is no one that since we have our recovery rate here, and that's our R. So for us to get the number of those that we recover, you just multiply it by the number of effectives. So I don't think there's need for using our the 8 days there. Okay, that's my own judgment. I might be wrong. So, but that's how that's how I will solve it if I'm to solve it.
Okay.
So, but this question now is for $1,000. This last one now is for $1,000. Are we ready?
Which one?
Give me three. Give me 3 reasons. They say 1 reason, but I want 3 reasons.
Because it assumes that everyone
Everyone
is.
is accessible.
Give me 1 reason why the SAR model has.
That's the only way it was.
Why? Number 1,
Because
give me 1 reason.
RO assumes that every member of the population is susceptible to infection.
In the COVID-19, no.
Okay. Now
is correct.
that's
One.
one. No.
One. Number 2. What's the other one? Number 2 now.
It's only what you told us.
No, I said
Chibuzo, what did
3
you say?
reasons. I said 3 reasons.
It doesn't account people who have recovered. It doesn't account for those that have recovered.
What? Sorry, I didn't get that.
It does not take into consideration those that have been vaccinated.
Okay.
No, because from the formula, BS I minus RI. So R includes both the recovered and those that are immune to it. So it takes into account. What else again? Let me see those get it. There's a keyword. Let me see. So does it mean yeah? Hello?
We can hear you. We can hear you.
I want people to answer now. I want to give $1,000.
Dr. Anthony, people are Googling. They are just busy there.
Okay.
Sad. They are not nice.
All right. Okay, so
Sorry, Anthony, we can't hear you. We can't hear you.
Population. That means cognizance of the birth rate. Some model is assuming that means it's assuming so it don't take into birth rate and the death rate. Like COVID-19, the birth rate might increase or the death rate might
I can't
might
hear.
increase. So I can hear you now.
No.
It was breaking.
Okay, so I was saying that the SAR model assumes a closed population. It assumes a constant population. All right. So it does not
A close population, a
account
constant
the birth rate,
population. Which one?
and that means the changing dynamics of the birth rate and the death rate. It doesn't take that into account. So it assumes that the population is what? Constant. They are the same. They are the same. Whether close or constant, it's same thing. That means nobody is not. Nobody is moving in. Nobody is dying. Nobody is so
basically, in this example, the
hello. Hello.
Hello.
Hello. Yeah. So I said.
So basically, for example, if there's 10,000 people in a town,
yes.
the SR model is in the SR model, the 10,000 will always remain 10,000. It does not take into account any newborn deaths and any deaths.
Exactly. Correct. Yeah. So and then it also assumes that the rate of recovery is constant. So this for some model, our gamma is constant. Okay, and it also assumes that our R is constant too. Our okay, so if you go to the critique of SAR model, you will see a lot of critique of the SAR model.
The line is just breaking and making the whole thing not to flow.
Right? So if you want
I cannot hear anything.
Actually, your connection is very bad. We can't hear anything.
Okay, so hello, hello.
Yeah, we can hear you better now.
Okay, so I said.
Now it's breaking again.
Okay, so I said in summary, I said in summary, the sum that assumes a constant population. It assumes that the recovery is constant. It assumes that the bet it doesn't take into account the bet rate and the death rate. All right. So those are the basic assumptions of the SAR model and the weakness. All right. So I'm going to stop here. I'm going to stop here, and then let's ask questions. Any question before we call it a day? We have spent so much time.
So basically, what I understood from today's session, that the SI model is the most important model, which we will need to learn.
Yes. For now, yes.
So at least
there are
session
other models. There are other models, but the basic one you need to know is just the SAR model. Okay, for now, yeah. That's all you need to know. Just
So
understand how all the equations flow into each other. Understand how they relate. Okay, so write down all those equations. See whether you can reason them out. You know, like normal reasoning, so that anyhow the question comes, you'll be able to derive it. Okay. So that's it.
So using this model, we should be able to answer most of the questions which will come in the exam paper.
Yes. If you're able to do what I did today, understand how to derive it from the whole graph and everything, you are good to go. You're good to go. So if you go back now and read your lecture note now, it will make more sense. If you go back now and read it again, it will make more sense. Okay, so there are other models, and then but the SAR is just the most important for now. Yeah.
What's the difference between the SIR and the SI model?
Okay, so the SI model does not take into account the recovery rate.
Okay.
Yeah, so the SIR is an improved version of SI of the SI model. Then there's also SEIR. So SEIR is an improved version of the SAR model. Okay, so but that one I don't know it, and I don't know it for now. So let me learn only the SAR model for now. For now. Yeah. So that EDI is for exposed. So that model talks about those that are exposed. It takes into account that. So there are various versions, but the basic one that you need to understand is this SAR. So from SAR you can build other versions that you maybe as after MPH you can if you want to go deeper in epidemiology, then you can learn about all those ones. All right. So good luck and God bless everyone.